Now that we have the concept of what an antiderivative is, we want to establish some simple properties that will make it easy for us to find antiderivative. So in conjunction with these rules that we came up with, right, these kind of basic antiderivative rules, if we can have some properties, then it can really expand the types of functions for which we can find antiderivatives, right? And it turns out that the properties that we're going to discuss now come directly from the constant multiple, the sum, and difference properties for derivatives. They translate directly over here. So this is actually a theorem, right? And I'm not going to give the proof because it's essentially the proof is we gave the proof for the sum and difference and constant multiple rules for derivatives, and the proof for this is simply restating those rules, right? But in terms of anti-derivatives, right? So here's the theorem. And it's this, so suppose f of x and g of x, right, are antiderivatives. So are antiderivatives of little f and little g respectively. All right, so that means if I differentiate big F, I will get little f, and if I differentiate big G, I will get little g, right? And then I'm going to need a constant for one of these rules. So also let k be some real constant. All right. So here's our first property. And basically, so I'll write it down and then we actually say, or in fact, while I write it down, we will simply just kind of illustrate exactly what the property is saying. So let's say I have to find the antiderivative of this constant, let's say times f of x. So k times f of x, right? Now remember, if we had to differentiate a constant times a function, we were essentially able to just bring the constant down, or another way to think about it is that we had the ability to factor the constant out of the derivative, right? Well, we can do the same thing here. We can factor the constant out of the antiderivative. So I can pull k, right, and put it in front, right? So this ends up being k times the antiderivative of little f of x dx. But I know what this is. This part here is my big f of x, right? So this would be my big f of x, and then I have my plus c, right? So this is the constant multiple rule for antiderivatives, right? So this is the constant multiple rule, right? But now for antiderivatives, and it looks very similar, and it's meant to look very similar to the constant multiple rule for derivatives, right? B is basically saying, well, what if we were to add little f and little g, and then try to find the antiderivative of the sum? So what if I had to find the antiderivative of little f of x plus little g of x dx? Well, if you remember, once we learned our basic rules for derivatives, then we could apply those rules for derivatives term by term if there was a sum and also a difference, and we'll get to the difference in a second. But basically, if you have multiple terms in your function, well, you can find the antiderivative of each term separately. So in other words, you can split this single antiderivative into the sum of two antiderivatives. By that I mean find the antiderivative of f of x dx plus times the antiderivative, or plus the antiderivative of g of x dx. And then we know that the antiderivative of little f is big F. We know the antiderivative of little g is big G. So now we can add those two together and get the antiderivative of f plus g, right? So this is big F of x plus big G of x, and of course we can't forget our constant of integration. And this is the sum rule, meaning when we have the sum of two functions and we're trying to find their its antiderivative, right? The antiderivative of the sum is the sum of the antiderivative of the individual terms. So we call this our sum rule, right? Just like how we had a sum rule for derivatives. And then similarly, I could simply change that plus sign to a minus sign. We'll change these three plus signs to minus signs, and then we will have the difference rule. So let me write that down. So the antiderivative of f of x minus g of x with respect to x, well, again, mentally, we can think of it as the antiderivative of f of x with respect to x minus the antiderivative of g of x with respect to x. So then now, using what we know about the relationship between little f and big F and little g and big G, we can write it down as big F of x minus big G of x plus c. And as you might expect, this is called the difference rule for antiderivatives, right? But as I said, essentially what we're doing, and we started doing this in our previous video, is we're looking at what we know about derivatives and we're restating it now in terms of antiderivatives. And that's how we're able to quite easily come up with these three very basic but very important properties for antiderivatives, right? And what this allows us to do is it allows us to find the antiderivatives of lots of different functions now, because we can have a function being multiplied by constants, in fact any constants, and then we can find this, we could be adding functions together or subtracting functions, and then we can still do the anti-differentiation process term by term, right? So let's do a few examples illustrating this, right? So let's do some examples here. So starting with example 1. So I'll just write down what we're computing. So let's say we have to find the antiderivative of 2x plus 5x squared minus 3 cosine of 4x plus e to the negative 2x dx, right? Now previously we went through and we derived antiderivative rules for power functions, these two, right? We came up with antiderivative rules for sine and cosine functions like this, and we also came up with a general antiderivative rule for exponential functions. So we'll get to use those rules in this case in addition to these properties, right? Now, as far as using the properties are really mental steps that you apply as you work through the solution to a particular problem. Usually you don't state the properties as explicitly as I'm about to, but I'm going to do it in order to show you how each of these rules are being applied. And the first rules that I will apply are the sum and difference rule. So this function right here, whose antiderivative we're trying to find, has 4 terms. So I'm going to break up this big antiderivative into the sum slash difference of 4 antiderivatives. So in other words, mentally I think of this as the antiderivative of 2x plus, I bring down my plus sign, the antiderivative of 5x squared, right, minus the antiderivative of 3 cosine of 4x dx, and then finally plus, bring down this plus sign, the antiderivative of e to the negative 2x dx. All right. So for the first one, our power is 1, right? But if you look, we also we have all these constants, like the x function is being multiplied by 2. But the constant multiple rule now says I can factor out the constant. So I could put this 2 outside and then have the antiderivative of just x to the first power dx. Similarly, using the constant multiple rule, I can factor the 5 out. So I'll have 5 times the antiderivative of x squared with respect to x. Keep going. Minus, factor out the 3. And then I'll have the antiderivative of cosine of 4x with respect to x. And then here, this coefficient of the e is 1, so I don't need to factor anything out there. So I'm just going to bring down that antiderivative e to the negative 2x dx. Right? Now I get to use my power rule for antiderivatives here and here. So let's do that. So I'll have 2 times. When I apply my power rule, I will add 1 and then divide by the new power, right? So this becomes 1/2 x squared, and then keep going. Plus, bring down the 5, and then it's 5 times. Now my power is 2. The power rule for antiderivative says add 1 to this power and then divide by the new power. So this is 1/3 x cubed, and then keep going, bring down the minus 3 times. Now for the cosine function, the cosine of 4x, we're going to divide by 4, or equivalently multiply by 1/4. And I know that when I differentiate sine, I will get cosine, so this will be the sine of 4x. And then lastly, plus. Now, the rule that we came up with for the basic exponential function and its antiderivative is that whatever this constant is, this coefficient of the exponent, we end up dividing by. 'Cause essentially, it's the reverse of the chain rule, right? That's what this is as well. It's the reverse of the chain rule. And then we're going to end up getting 1 over negative 2 e to the negative 2x. And then we can't forget our plus c, right? So this is kind of the unsimplified answer to this particular problem. Let's go ahead and simplify. So we have 2 times 1/2 is 1, so this is simply x squared. 5 times 1/3, so that is 5/3 x cubed, minus 3/4 sine of 4x, and then what I'll do is I'll take this negative and put it in front, so I'll now have a minus 1/2 e to the negative 2x plus c. And this function now, if I were to differentiate this, I would end up getting back my original function, right? And that means that x squared plus 5/3 x cubed minus 3/4 sine of 4x minus 1/2 e to the negative 2x plus c is the antiderivative of this function. All right? So again, it just shows you that the constant multiple, the sum, the difference, those basic rules are very, very helpful. Now, let's do another example, right? And then we will wrap up by looking at some other antiderivative rules that involve like other trig functions and then some inverse trig functions. Those are very, very important. But let's take a look at another example let's say we have 4 over x minus 5 over x cubed plus 10 with respect to x. So now we have to find the antiderivative of this, right? Well, this, and remember the function whose antiderivative we're trying to find, it is called the integrand, right? This integrand has three terms: the 4 over x, the 5 over x cubed, and the 10. So let's split this up into three separate antiderivatives. So like that, and that, and that. All right. Okay, so do we have constants? Yep, we have constants that we can factor out. I can factor out the 4 out of the first antiderivative. So 4, and then that leaves me with 1 over x dx. Factor out the 5, so I have a minus 5 outside, and then I have 1 over x squared dx. And then here I can factor out the 10, right? And I can write this as plus 10 times the antiderivative of, I could do the 1 dx, but this is when you factor out the 10, the 1 is understood even if you just put the dx there, because the way you're interpreting this is it's 1 times dx, right? So even without the 1 there, it still would be interpreted as just 1 dx. All right, so let's see if we can do this. Now this is that special case of the where we are finding the antiderivative of 1 over x, and that's going to be our natural log. So this will be 4 times the natural log of x. Now for this one, you have to be careful. This is no longer a natural log because this can be rewritten as a power function where the power is not equal to -1. It's only when the power of your power function is equal to -1, that's when you end up using the natural log for your as your antiderivative. Here, what we are able to do is rewrite that power function as x to the -2, right? So we can rewrite it using our basic property of exponents, bring up that denominator, and change it from a positive 2 to a -2, and then I'll continue to write this like that. All right. So now let's find the antiderivative of x to the -2. Well, there let me bring down the natural log of x. So we have minus 5. Then it's going to be add 1 to the power. So that makes it -1. So then it's going to be 1 over -1 times x to the -1 plus 10. And what do we do here? Well, there are lots of ways you could do it. You could ask yourself, well, what function do I know when I differentiate it will give me a 1, right? When I differentiate x with respect to x, I'll get a 1. But it actually turns out that this is really just a special case of the power rule, because I can think of 1 as x to the 0. So if I think of it as x to the 0, and when I add 1 and divide by 1, I'm going to end up getting like this, 1 over 1 times x to the 1. So it works out the same, right? So whether you, again, use your knowledge of derivatives and ask yourself, what function, when I differentiate it with respect to x, will give me 1, or if you want to express 1 as a power of x and then apply our power rule, it works out the same. And then we can't forget our plus c, so put our plus c there. So we'll end up getting 4 times the natural log of x. Now I have -5 divided by -1, so that's a positive 5x to the -1. And then all of this simplifies to 10x and then plus c. So then finally, now if you want to write this without negative exponents, our final antiderivative is 4 times the natural log of x plus 5 over x plus 10x plus c. All right. So there are just a couple examples that show you how useful these properties are, and the properties, what they allow you to do is essentially break something that seems a little bit more complicated down into simpler, more basic antiderivatives that we're able to reverse what we know about differentiation. Right. Now here I'm just going to go through a couple other important rules for derivatives and then restate them in terms of antiderivatives, right? So I'll just say, let me just kind of entitle this other important rules of anti-differentiation. Right. So again, these are some other ones that are helpful. We could write down a whole ton because if you think about it, we've differentiated many functions up to this point, but here we're really just starting with the basic ones, right? So for instance, here is and I'll just go through and kind of list them. Let's say I have the antiderivative of secant squared times ax with respect to x. Well, then I would have to ask myself, what function do I know that has a derivative of secant squared? And if we think, and if we think, and if we think, we come up with tangent. So we know that the tangent of x, if I differentiate it, will give me secant squared x. But what about this extra constant right here? Well, we handle it the same way we end up handling the previous constants that we had. We end up having 1 over a times the tangent of ax plus c, right? And this again is a rule. So when you see something, if you have a term that involves secant squared, and you have to find its antiderivative, that's going to end up being tangent, and then you have to adjust for any additional constant you might have, right? Let's do one more trig one. I'm not going to do all the trig ones, but let's say we have something like secant ax times the tangent of ax dx. And we want to find its antiderivative. Well, we know that the derivative of secant x is secant x times tangent x. So that means the antiderivative of secant ax times the tangent of ax, and that's going to be, again, that familiar 1 over a, and then we'll have our secant of ax plus c. The other two that I want to state, or I guess three, have to do with the inverse trig functions. And these are three that are really useful. And it's stated like this. So if you have the antiderivative of 1 over a squared plus x squared dx, this one is the famous arctangent. Now, if you have a constant here, right, and the reason why it's written as like the constant squared is that it makes it a little bit easier to state the property or the rule on this side. So the rule is this: it's 1 over a, so essentially you take the positive square root of this number, right, and then you'll have your arctangent, and then here you'll have of x over a, right, plus c. Now, this negative 1 here is not a reciprocal. In fact, I've been in favor of writing, arctangent or inverse tangent function, the inverse tangent function, and using this notation, right? So there's that one. Let's do the one for arcsine. And for if you think about the derivative of arcsine, you end up with something that looks not exactly like this. It's typically not stated in this form with derivatives, but here with antiderivatives, we're allowing for other types of constants here, right? So in this case, This is the only one. This is the one where you have to be careful that you don't end up getting this one doesn't have a 1 over a in front, and it's because of the square root in the denominator here. So there's a bit of algebra that could be done to show that this antiderivative works out to be arc sine of x over a, and then you have your plus c. And again, remember, this is not a reciprocal. This is the inverse sine function, or the arc sine function of x divided by a plus c. So these are a little bit more, I wouldn't say complicated, but just a little bit more involved. And you just have to be careful how you apply them. But knowing that these rules are there, and knowing, okay, I need to look out for these forms, then make sure you do so, right? And let's just do a couple more examples and then wrap this one up. So let's say we have 2 times the secant squared of 5x minus 10 secant x over 2 times the tangent of x over 2 dx. Right? Okay, so let's say we have these two. Or actually, this antiderivative that has 2 terms. Well, let's split these up into 2 separate antiderivatives. So we're going to use our difference rule and the constant multiple rule. Let's apply them all at once. So this is 2 times the antiderivative of secant squared of 5x dx, and then minus 10 times the antiderivative of secant of x over 2 times the tangent of x over 2 dx. Right? So you can see this one is set up perfectly for our secant squared, and we know that the antiderivative of secant squared is going to be tangent, but here I have this extra constant. So since I am anti-differentiating, I am going to divide by this constant instead of multiplying by the constant. So I end up getting 2 times 1 over 5 times the tangent of 5x, right? So that's from the first one. Bring down the minus 10. Now for this one, the x over 2, the way you want to interpret x over 2 is that it's 1/2 x and 1/2 x. So in this case, the constant here is 1/2. So the rule is going to be 1 over 1/2. And then I see that secant tangent pattern, and I know that the antiderivative of secant times tangent is secant, and then I keep that inner function. So if I wanted to write it, I could write it as the 1/2 x, that's fine, or you could keep it as the x over 2. But the important thing here is to make sure that we recognize that the constant that's multiplying our x is actually 1/2. So that's why we have those 1/2 in the denominator right here. And then we end up with our plus c. So then our final answer is 2/5 times the tangent of 5x minus 1 over 1/2 is 2. 10 times 2 is 20. So this is minus 20 times the secant of 1/2 x plus c. Right, there we go. And then our last example is going to involve our inverse trig function. So let's say we have the antiderivative of 4 over 5 plus x squared minus 3 over the square root of 4 minus x squared dx, right? So these you want to look out for. Like down here, you want to look out for a constant plus x squared, or your variable squared. And then over here, again, you want to look for the square root of a constant minus your x squared. Now, the 4 and the 3 that are the numerators here, these can be factored out, right? So in other words, this is equal to 4 times the antiderivative of 1 over 5 plus x squared dx minus, factor out the 3, and then times the antiderivative of 1 over the square root of 4 minus x squared dx. And in this case, so let me just do a little bit of a calculation here. So based on how the rule is normally stated, your a squared here is 5, and then taking the positive square root, we get that a is root 5. And then for this one, a squared is 4. Taking the positive square root, we get that a is 2. So now I can write down the rule that gives me the antiderivative for each of these. So this is 4 times, and then this is the arctangent, so it's 1 over root 5 times the arctangent of x over root 5, and then bring down the minus 3, so minus 3 times, and then this one is arcsine. But arcsine doesn't have the 1 over a in front, so you just have to be careful with that. And then this is so arcsine of x over, and in this case your a is 2, so like this, and then we have our plus c, right? And there's not much we can do to simplify this. Really, the only thing we could do, if you wanted to do anything, was to write the 4 times 1 over root 5. First, you could rationalize and write this as a single fraction. So when it's rationalized, it becomes 4 root 5 over 5 times arctangent. We could rationalize this too and write it as root 5x over 5. You could do that. And then this one, there is no rationalization needed. So then it's minus 3 arcsine of x over 2 plus c, right? So I would say the ones that involve the inverse trig functions, your arctangent, arcsecant, arcsine. There is one for arcsecant. I'm not going to state that one right now. And then also your natural log ones. Those you have to be careful of. Just to look for those 1 over. Look for the ones that you can't rewrite easily as a simple power function. And then make sure you apply the appropriate rule. So there we go. So we're kind of building, getting used to this idea of working backwards. And again, I'll continue to stress it, that if you are relatively comfortable with the process of differentiation, if you know the basic rules, right? Working backwards with our basic rules for anti-differentiation shouldn't be too difficult at all. But as with everything in math, it comes with practice. So even if it's difficult at the start, push through it, keep practicing, do lots and lots of examples, and you'll certainly get better and better at it. And with that in mind, I'll see you in the next video.